Hey ladies and gentlemen, and welcome back to Physical Science. I'm Mr. Parkin, and today we're going to pick up last week where we left off. First off, we want to talk about the standard again. The standard is apply Newton's laws to predict the resulting motion of a system by constructing force diagrams that identify the external forces acting on a system. All right, so as a review, last week we went over Newton's first law, we went over Newton's second law, and then we stopped at universal gravitation. So Newton's first law just says that an object in motion will stay in motion, or an object at rest will stay at rest unless it's acted upon by an unbalanced force. So if we're out in the middle of outer space where there's no friction, no forces on this object, and we push a ball, that ball is going to go in the same direction with the same velocity forever or until it comes in contact with an unbalanced force. So it gets near a planet and falls into a gravitational field. Or if we sit this clicker here and we don't touch it, it's not going to move until we touch it. All right? I just place an unbalanced force. Also, the first law is called the law of inertia. We talked about inertia. Well, I don't have it up here. Inertia is mass in motion. So the larger the mass is, the harder it is to change its motion. We talked about when you're sitting in a car, when that car takes a left turn, you want to go right, or when that car takes a right turn, you want to go left. That's because inertia is resisting your motion. So what's happening is you're trying to stay in the same spot, but because that car is going right, you're going left. And we also saw an animation where a car, it was just an animation, where a car hit a wall and then the human comes out, probably the test dummy comes out. That's because, let's say that car is going 80 miles per hour and it hits that wall, you inside, or that crash dummy inside the car, is still going to want to maintain 80 miles per hour and it's going to fly out that car. And we talked about that's why seat belts are so important. Then we went on to Newton's second law. Newton's second law simply states the net force on an object is equal to that object's mass and the acceleration of the object. And we also said we can say F equals ma for short. All right, we talked about a force. A force is just a push or a pull. And a force can be anything like friction, gravity. We said that the Newton, also represented just by the capital N, is the units of force. All right, so you have a force of 5 newtons pushed on you, or I'm going to push this car with 5 newtons of force to get it to start rolling, okay? But then you also have the types of friction we talked about. So we talked about friction was the contact between two surfaces, okay? Contact between two surfaces. You have sliding friction, so if I slid this remote all the way across the table, it would slide, causing sliding friction. We also talked about rolling friction. So again, if I took that car, it has 2 wheels. It's going to roll across this surface, causing rolling friction, okay? Fluid friction or viscous friction, I wrote it on the board last week. Fluid friction or viscous friction is something that goes through a fluid. So a fluid can be anything like water or even air. Air is a fluid. So an airplane flying through the air has fluid friction. Or you saw me drop these pennies through the water. The regular size penny dropped pretty fast, but then the penny that was flattened by the train, it dropped slower. That's because surface area, the total surface area of an object, is what makes friction greater or smaller. So the bigger the surface area, the more friction that you feel on an object. Kilogram. A kilogram is the unit of measure for mass. We talked about mass was the amount of matter in an object, okay? And then For the last 2 weeks, this will be the third week that we've talked about gravity. Gravity is just the force that is felt between two objects. And on Earth, gravity causes us to fall straight down, okay? So we're going to pick up this week where we left off last week, and that was right here. So we all know the story about Isaac Newton sitting under an apple tree and the apple hit him in the head, and that's how he discovered gravity. He didn't just get hit by the apple and all of a sudden, oh, gravity, here it is. You know, he had to work on it. But the universal gravitation is this. All right, you can find the force of gravity, which on Earth, the force of gravity causes an acceleration of 9.81 meters per second squared. The force of gravity is equal to the gravitational constant times the mass of object 1 and the mass of object 2 divided by the length between those two masses, okay? So the gravitational constant, that means a constant means it's the same throughout. Okay, the gravitational constant, no matter where you are in the universe, this is what you use. It's 6.674 times 10 to the negative 11 Newton meters squared divided by kilogram squared, okay? So you won't need to really know much about this now, so this is just information that you don't have to carry on. The two main things that Newton discovered that you needed to know were the masses of the two objects and the distance between them. So if you have two masses, so let's say the mass of the Earth and the mass of the Moon, and you want to know the force of gravity between the Moon and between Earth. If you know the mass of the Earth, which scientists do, and you know the mass of the Moon, which scientists also know, then you can find out the force of gravity if you know the distance between them. And again, scientists do. So that's just how they do it. So they can find the force of gravity between the Sun and Jupiter. They can find the force of gravity between the Sun and Neptune. It's just these two masses, okay? Moving on from there, I wanted to review Newton's second law, okay? And remember, Newton's second law, and we're going to use this later on today, that's why I want to review it, is simply the force, the net force on any object equals the mass of that object times its acceleration. And I also showed you this. So the force on an object equals the mass times the acceleration. So remember, I said if we want the force, just cover up the F, and that will give us mass times acceleration. If we want to know the acceleration, cover up the A, and it's force divided by mass, and then the same for the M. So if you'll direct your attention to the slideshow real quick, number 1 says what acceleration will result when a 12 Newton net force applied to a 3 kilogram object. What acceleration will result when a 12 Newton net force is applied to a 3 kilogram object? So now we're just going to plug in. So we have a 12 Newton net force, and it's applied to a 3 kilogram object. Now what's the acceleration? That's what we're trying to find. So we can solve this algebraically, which you just divide by 3 on both sides, and the acceleration will be 4 meters per second squared. Or if you weren't sure how to do that, all you had to do was cover up your A, and that would give you force divided by mass. All right, so you can do that same thing for a 6 kilogram object if you would like. And instead of this 3, you can plug in a 6 there, and then your acceleration would be 2 meters per second squared. Number 2, yes, we're going to do all 4 of these. A net force of 16 newtons causes a mass to accelerate at 5 meters per second squared. So we don't know what the mass is, so we're going to put an M for mass. Causes an object to accelerate 5 meters per second squared. So if I don't know how to find this M, cover up the M, it's force divided by acceleration. So 16 newtons divided by 5 meters per second squared. Get our fancy calculators out, remember? And it's 16 divided by 5 equals 3.2 kilograms. So 16 divided by 5 equals 3.2. All right, 2 more, and then we're going to move on from these problems. How much force is needed to accelerate a 66 kilogram skier at 1 meter per second squared? So we're looking for the force, and we have a 66 kilogram skier, and we want to accelerate that skier at 1 meter per second squared. All right, cover up the force, mass times acceleration. So that's pretty simple. It's just 66 times 1, 66 newtons. All right, simple as that. Now, number 4 may seem pretty simple, but it's actually a very important one for today. We're going to be concentrating a lot on this concept today. It says, what is the force on a 1,000 kilogram elevator that is free falling at 9.8 meters per second squared? Remember that the force of gravity, or the acceleration of the force of gravity, the acceleration of the force of gravity is 9.81 meters per second squared. So there's nothing causing this elevator to fall except for the force of gravity in this case. So we have 1,000 kilograms times 9.81 meters per second squared. So just take that right there, or in this case 9.8, and it'll be 9,800 newtons. And if you wanted to keep that 1 like I wrote on the board earlier, it would be 9,810 newtons instead of just plain old 9,800. All right, so that just shows you how to apply Newton's second law, force equals mass times acceleration. All right, now that we have done that, we're going to move on and just review forces just a little bit more. So we talked about a force is just a push or a pull on an object. So there are different types of forces. This is just 4 examples. This isn't all the forces in the world, but gravity is the force between objects. So this ball falling to the earth, or the moon orbiting around the earth, that's also gravity. We have static electricity. You know, when you wake up in the morning and your hair's crazy and it sticks to everything, or when your clothes come out of the dryer, that is the force of electrons clashing together, okay? The force of electrons. The magnetic fields that you see. So if you put a magnet on the refrigerator, the force of the magnetic field, that's why they stick. And then friction. So any type of athlete, basketball, football, this biker just walking along the ground, driving a car, you all experience friction. All right, so we're going to talk about the final law of motion. Newton's third law of motion that we're going to discuss is the third law of motion, and that plainly states that for every action there is an equal and opposite reaction. Now I'm talking about forces here. I'm not talking about if you act up, you know, you're going to get switched by your parents. That's not the type of action I'm talking about here. I'm talking about if I place a force down on this desk, it's said by Newton's third law that the table or the desk is also applying a force up on me at the same magnitude. So think of sitting in a chair. According to Newton, whenever objects A and B interact with each other, the forces, they exert forces on each other. When you sit in your chair, your body exerts a downward force, and the chair also exerts an upward force, okay? So just sit in a chair. Here's another, a force between the chair and your body. These two are called action-reaction. So you sitting in the chair is the action, and the chair pushing up on you is the reaction, okay? So a fish swimming. When a fish swims, it flaps its little fin, pushes water back. The water that it's pushing back propels that fish forward. Action is the flapping, the reaction is the water pushing the fish forward. Kind of get the idea? Another example is a bird flying through the air. The action is the bird flapping its wings straight down, and the reaction is the bird flying up, okay? And there's just a little animation. So a more of kind of something that you could probably understand is when you swing a bat and that ball hits the bat. Okay, that is actually an action-reaction. The ball is hitting the bat and the bat hits the ball. Okay, action-reaction. And that's more of an active kind of Newton's third law. All right, rockets going into outer space. So you know that there has to be a ton of force to cause this little explosion, this combustion that's happening out of a rocket. So when those gases are forced out of a rocket, like shown in this slide, the gas pushes down on the Earth, causing the rocket to propel up. So the action is the gas is pushing down from the rocket, and the reaction is the rocket accelerating into outer space. All right, so now our goal is to put all of this together. All of this together. So basically, we know that a car has to accelerate somehow. We say, okay, to accelerate a car, you have to press the gas. All there is to it, right? Just press the gas, nothing else happening. Well, that's actually wrong. These wheels right here, they're actually spinning. When these wheels spin, they are pushing, in this case, the table behind it. They're pushing the table behind it, causing this car to go forward. So the action is these wheels that are pushing on the table, and the reaction is the car moving forward. All right, so the same thing can be applied here. I don't have to put any force at all on this car. I don't have to put any force at all on this car to get it to slide down this ramp, right? What does that for us? The force of gravity. All right? So now that we kind of have an idea about the second and third law, don't forget the first law, but now we're going to concentrate on how the second law and the third law connect. So, are there any forces acting on this car when it's just sitting on the table? If you said yes, you're correct. For one thing, there's static friction keeping this car immobile, meaning it's not in motion, and there's also gravity pushing it downward. So we're going to talk about these force diagrams real quick. So we have a 1 kilogram car sitting on that table. That car has a mass of 1 kilogram. So let's just say this is the center of mass of that car. We know that gravity is pushing downward. Okay? The force of gravity on that car, how do we find just the force of gravity on that car? Well, we have the mass of the car, which is 1 kilogram, okay? It's 1 kilogram, and we know the acceleration due to gravity is 9.81 meters per second. So if you said that the force acting on this car is 9.81 newtons, you would be correct. All right, this right here is a force. But did you know this is the same force as if you were to step on a scale at home? Did you know that? So what this does, what the force of gravity does, it takes the acceleration due to gravity combined with a mass and it gives you a force. Well, weight is actually a force. So you could have actually said weight equals 9.81 newtons. Because you take your body's mass, you step on that scale, and it gives you a number. However, the difference is we, here in America, we use pounds. Pounds is weight, and it's also a force. All right? So do not get pounds confused with newtons, all right? So if you have a question about the difference in how we see weight and the difference of the force of weight, that is your answer. So the force of weight is newtons, okay? What about this car rolling down this ramp? What about this car rolling down this ramp? Well, we have a force going this way, which is it's the force of gravity that is parallel to the force parallel to gravity, but it's caused by gravity, okay? Gravity goes straight down. This car didn't go straight down, but the reason that car goes is gravity, okay? But is this car moving? The car is moving. So if the car is moving down, then we have another force that is going up this way. All right, let's try to talk about that real quick. So again, we have a car, and it's 1 kilogram. Gravity always goes straight down, okay? Always goes straight down. Force of gravity equals 9.81 newtons. In the case that the car was sitting on this table, do you remember we said that for every action there's an equal and opposite reaction? Since there's a force on this table right here, that means there's also a force going straight up. This would be called the normal force, and it would be equal to gravity in this case, 9.81 newtons. Okay? So this would be called the normal force. The normal force, it is a force that acts perpendicular to a surface. That means it forms a 90-degree angle or a right triangle or a right angle. All right, so now we had this car sliding down this ramp, okay? I'm going to draw this imaginary ramp. This imaginary ramp is here showing that the car is going to have this motion. Why does it have this motion though? Well, remember that the car is sitting on this surface. And if you remember, the surface pushes back up. Well, it's not going to go straight against gravity. It's going to come this way. The normal force is going to come this way. The difference between the normal force, ghosts, the difference between the normal force and the gravity is causing this cart to accelerate down this ramp. I better not see any memes on Facebook going around of me jumping when that periodic table came around. So friction is going to be traveling in this direction, the force of friction, but since it's on a slope, it's not going to be enough to overcome the motion. All right, so today we went over Newton's third law. For every action, there's an equal and opposite reaction. We went over Newton's second law. The net force on an object is equal to mass times acceleration. And then also we talked about force diagrams. All right, next week we're going to be here talking about energy. I hope you all have a great week. Stay safe.